Welcome to this video on the quantum gravity threshold principle. We will explore a framework that defines the domain of validity for quantum superposition, proposing a model of complementarity rather than unification for quantum mechanics and general relativity. Quantum mechanics rests on superposition, but its universality has never been tested under strong gravity. The quantum gravity threshold principle proposes that superposition is bounded, scaling with gravitational strength. Beyond the threshold, spacetime curvature forbids wave function splitting, leaving general relativity to govern exclusively. For a century, physics has pursued unification, assuming superposition is universal. Yet experiments confirm superposition only in weak gravity: photons, electrons, atoms, and molecules up to about 2,000 atoms. Universality under strong curvature remains untested. This is the gap Q-GTP addresses. Gravity requires no threshold principle. Neutron interferometry shows gravitational phase shifts. Atomic clocks redshift, depending on potential. Even photons bend around stars. Gravity acts universally across all scales. The limitation lies not in gravity, but in quantum mechanics. Q-GTP states, quantum superposition exists only below a threshold defined jointly by particle size and gravitational strength. Beyond this threshold, curvature forbids wave function splitting. The governing relation is delta E underscore G times T less than or equal to T, gravitational self-energy difference times lifetime bounded by Planck's constant. This curve shows how superposition lifetimes shrink as gravitational self-energy grows. In the quantum regime, small delta Eg yields long lifetimes. In the classical regime, large delta Eg drives collapse, with T approaching zero. Curvature compresses quantum lifetimes, forbidding superposition beyond thresholds. Strong gravity makes quantum objects inherently harder to split. Superposition ceases under gravity curvature. When we try to split a quantum system, we are asking spacetime itself to hold two distinct curvatures at the same coordinates. General relativity treats curvature as dynamic geometry, not a backdrop. Two incompatible dents cannot coexist in the same place. The split fails before it begins. Splitting mass means splitting its gravitational field. For photons, the energy cost is negligible. But for macromolecules, the required energy scales with mass squared. Under strong curvature, the universe cannot supply enough localized energy, and coherence collapses instantly. Quarks are confined by the strong force. They cannot be isolated. In the same way, wave functions are confined by gravity under high curvature. Attempts to separate them snap back violently, making superposition physically impossible. Penrose begins with superposition and asks how gravity collapses it. Q-GTP inverts the logic. Gravity resists the split from forming at all. Collapse is obsolete. The split is structurally forbidden at the outset. Splitting a drop of water is easy in zero gravity, but at the ocean floor, immense pressure prevents separation. Likewise, extreme spacetime curvature acts as environmental pressure, forbidding quantum splitting from ever taking hold. Thresholds scale with gravity. In microgravity, superposition extends beyond 2,000 atoms. On Earth, the baseline sits near 2,000. In centrifuge environments at 2 grams, the threshold shrinks to about 1,000 atoms. Near black holes, thresholds collapse to zero. Superposition is entirely forbidden. This chart shows particle size against gravitational strength. The scaling threshold marks the quantum classical boundary. Superposition is permitted below the line. Collapse dominates above. Thresholds shift inversely with gravity, but never vanish until extreme curvature. Standard quantum mechanics assumes universality. Penrose objective reduction allows collapse, but still assumes universality. Semi-classical gravity treats gravity as classical. Q-GTP alone abandons universality, asserting thresholds scale with gravity, while gravity itself always acts. Just as Newtonian mechanics failed near light speed and was replaced by relativity, quantum mechanics fails under strong curvature. Q-GTP reframes QM as an effective theory valid only within thresholds. GR governs beyond. Together they are complementary, not irreconcilable. Q-GTP is testable. Large molecule interferometry can push beyond 2,000 atoms. Levitated nanoparticles probe mass-dependent thresholds. Centrifuge experiments test shrinkage under 2 grams. Space-based interferometry explores expansion in microgravity. Cosmological observations provide indirect evidence from black holes and the early universe. Q-GTP is testable. Large molecule interferometry can push beyond 2,000 atoms. Levitated nanoparticles probe mass-dependent thresholds. Centrifuge experiments test shrinkage under 2 grams. Space-based interferometry explores expansion in microgravity. Cosmological observations provide indirect evidence from black holes and the early universe. This diagram shows the domains of validity. Quantum mechanics applies in low curvature, general relativity and high curvature. The Q-GTP threshold marks the boundary. Qm and Gr coexist without contradiction. Unification is unnecessary. Superposition is bounded. Thresholds scale with gravity. General relativity governs beyond. Q-GTP reframes quantum mechanics as an effective theory, complementary to general relativity, eliminating the need for unification.